Hello everyone, today in this video we'll be discussing the second module of Automata and Theory of Computation. So in this module we have the topics of regular expressions and grammar and regular languages. Okay, so let's go through the topics one by one and discuss what the things are. Okay, so firstly we need to know what is a regular expression and the Kleen theorem. It's important from exam point of view, and applications of regular expression. Then we'll go to manipulating and simplifying REs, which is regular expressions, and then we'll look at regular grammar, the definition, and grammars with regular languages. Okay. Then we'll focus on the differences between the regular and non-regular languages, and what are the closure properties of regular languages. And the main important part is here, which is the pumping theorem. And here we have we have to show that a language is regular and not regular. Okay. For that we'll be using a theorem in which the three tests will be there. By using that we'll be checking if it's the means the language is regular or not. Okay. So if you like this video, hit the like button and don't forget to subscribe to my channel. Okay. So let's move on to the topics. And these are the previous year questions, and most of these questions will be solving in the theoretical explanation itself. So we will be coming back to these questions and we'll be having a discussion on this as well. So let's get started with the questions now. I mean the topics. The first one is, what is a regular expression? Okay. So before that, the regular expression generates a regular language. Okay. If you have an expression with us, we can generate a language. Okay. And finite state machines accept strings and patterns which are a part of regular language. Okay. So regular expressions are defined in a recursive way, which we'll be looking in the upcoming topics. And the regular expressions is formed using the alphabet set. Okay, as we have discussed in the previous module, that by using alphabet sets we can form an expression which is known as regular expression. Okay, and null is a regular expression as well as an epsilon. The difference between null and epsilon is that null means there are no strings. Okay, and epsilon means there is a string but it's empty. Okay, it looks similar but it's actually different. Okay. So here are some of the mostly used operations, which are concatenation operation, union, and star means repeated 0 or more times, plus means 1 or more times. Moving on, we have the language of which has a set of null. We'll have here null. Okay, if you have here epsilon, we'll have here epsilon. That means it defines a language that has no strings or just an empty string. Okay, if you have like C here, C means a single letter. So the language that contains the single one character string. Okay, which is C. If you have AB, you can write it separately. Both will be equal, and union also can be written separately. Now let's solve a question here. In this question, it's given that L is equal to W belongs to A comma B. This set it belongs, and it's star here. That means A and B can be repeated n number of times. And the condition is that the length of the string should be even. Okay. So to have a string which is even, what we can do is A union B here and A union B here. Okay. So because it's even, we need to have two letters which will be repeated n number of times, right? So the first letter could be either A or B, and the second letter could also be A or B. What are the possible combinations? AA, AB, BA, BB. So these are the four combinations which can be repeated n number of times. That means in the first iteration I can choose either of these, in the second iteration also I can choose either of these, and so on. Okay, so this is the regular expression for the given condition here, which is the length of the string should be even. Okay, the next question is, L is equal to W belongs to A comma B star. W contains odd number of A's. See, if the number of A is odd, that means at least one A should be there, 3, 5, 7 and so on. Means odd number should be there, right? So if I need to have one A, so A will be present here initially. Okay, that will be there for sure. Okay, and after that I need 3 A's. That means it's getting increased by 2, means 1, then plus 2 which is 3, then plus 2 which is 5 and so on. So I'll have 2A here which will be repeated 0 or more times, right? If I want 3 A's, what I will do, these 2 A's I'll repeat, and this A is already here, so 1 plus 2, which is 3. So 3 number of A is there. Also we need to include B. Now B can come here also, here, here and here. Okay, because the combination does not means the criteria does not restrict the position of B. B can be placed anywhere. B can be repeated once, twice, or even 0 times. So therefore we need to occupy all the possible positions of B and with a star in top of it. Okay, because it's not given that at least any B should be there or not, so it can be repeated 0 or more number of times. Okay, so therefore we have star on top of each B. Okay, the third one is L is equal to W belongs to A comma B star. There is no more than one B. See, there is no more than one B means 0 or 1 B should be there. Either 0 B should be there or 1 B should be there. No more than 1 B. Okay, means 2, 3, 4 B's are not possible. So for accommodating at least 0 or 1, we'll be using an epsilon here or B. So this will ensure that either 0 will be repeated or 1 will be repeated. Okay, and then we can have A at the starting position or in the ending position. And since there is no restriction on A, we can have 0 or more number of A's here, as well as it can be present here also. Okay, no two consecutive symbols are same, means the consecutive symbols which are occurring together should not be same, like AA and BB is not possible. So therefore we have AB here, which is repeated n number of times, means 0 or more times, starting with B, because B, then A, B, it will be there, and ending with A. Okay, because it will end with B here. If I want A, I can place here A. Okay, or what can be done is, instead of AB we can place here as BA, right? So it will be A, then BA, repeated 0 or more times, then ended with B. Okay, so this will ensure that the string which I am repeating here, it will have no consecutive symbols which are same. Okay, the next one is obtain a regular expression for the floating point numbers. So observe the format of floating point numbers. In this example we have a plus sign here, then a digit, then dot, then here also one digit. That's also a type of floating point number. In this one we don't have any sign here. Okay, this is also a valid symbol. Here we have E, and after E we have 1, right? This is one of the format, and we have negative number here, as well as between E and 1 we have plus here. Okay, this is also a valid format. Okay, and here we have the negative, then the digit E, and then here the digit. Okay, in between E and the digit we don't have any sign. Okay, so keeping in mind all of these combinations, we have to generate a regular expression which by using which we can generate each of these strings. Okay, so before starting, assume that a decimal number is in the form x or x dot y, where x is a digit. Okay, if it's like 7, it will be 7 here, or 7.4, 7 point, and y will be replaced with 4. So this is the format for representing a single digit or with a decimal. Okay, and we have the main format here, which is the first the optional sign, that means either plus, minus, or like empty, means nothing is present here, right? Those three are the possibilities starting with the number. Plus can be there, and no symbol, or negative. That's the optional sign here. Then the decimal number is of two forms, either x or x dot y. Okay, and after that we have the E here. Either E could be present or not present. If E is present, we can have the optional sign between E and the number, means after E, if E is present, number will also be there. Okay, and in between the E and the number, either there can be any sign or there cannot be any sign. So this we have written here, E and D, in between an optional sign. How to translate this into a expression? In this expression we will write here null character means nothing is repeated twice. I mean it, epsilon here means there is a possibility that there can be no symbol here, or there can be plus, or there can be minus. This is separated using a union operation. Okay, so this was the optional sign, which is the first part here. Second part we have x or x dot y. So x is represented by at least one or more symbols, plus is here, and epsilon union d plus means point d, means either d will go with epsilon or d will go with point d. This means that it will accommodate both the normal digits and the decimal points also. So if you want just the normal digits, we'll go with epsilon, else we'll go with d point d. There will have two digits in place of d. Okay. After that we have e here. Either e could be present or not present. So I've written here epsilon or the whole thing here. In this thing we will accommodate these possibilities. Here we will have e. Along with e we will have either a sign, optional sign, and along with that we will have a d here. D is the digit. Okay. So this is the regular expression for the floating point numbers. Okay. Moving on, we have the Kleen's theorem. So what does Kleen's theorem say? For every regular expression, there is an equivalent finite state machine. So given a regular expression, we can form a finite state machine. Let's see what are the basic rules. If alpha is C, which belongs to the alphabet set, then the FSM is nothing but this is the starting state, which have arrow here, and this is the final state, which is double circle. Okay. In between that, the regular expression is C here, and if the alpha is null, that means there will be no final state. There will be no final state means only the starting state will be there. Okay. And if alpha is equal to epsilon, that means there is a starting and the ending state are same. So that's why only we are able to travel from the starting to the ending state without passing through any other expression, right? Epsilon means empty string, so we are traversing from starting to ending point via empty string. Okay. So here's the difference. In the null string will have no final state. In the epsilon string will have the final state and the starting state as same. Okay, that's the difference. Moving on, we have the union operation. So if language of alpha is equal to language of beta union language of gamma, how can we represent this using a FSM? Okay, so first make the state here. Suppose that it's A union B. Okay, language of beta is A and language of gamma is B. Okay, first draw the diagram for means the finite state machine for A. Finite state machine for A will be starting state, which is S1, then A, then the final state. For B also it will be the same thing, S2, B, and then final state. Now how to make the union of both of these? To make the union, create a new starting state, connect via epsilon to S1 and S2. Okay, so this is S1, this is S2. Write down S1 here and S2 here. Okay, and then create a new starting state. Initially these two are the starting state, right? But we are creating a new starting state which is like S3, and then what we are doing is we are connecting this one with this one here, S1, and this one with S2 here via epsilon. Okay, so this is the how you do the union operation. Okay, in the same way we have concatenation, in which we will draw the states of A and B here. If it's concatenation, what we have to do is connect the ending state of this one with the starting state of this one. Okay, this is the ending state of A and this is the starting state of B. This is connected via epsilon. Okay, so this is how you do the concatenation. And finally we have the clean star. That means repeated n number of times. Suppose that this is A here. If A is repeated n number of times, do 3 steps. First create a new start state here, which will be the S2, and then connect it with the starting state of A. Okay, make a new starting state, connect with the starting state of A, and from A draw back epsilon to S1. Okay, we did 3 things. First make here a new accepting state, and then connect with S1, which is the starting state of A via epsilon, and then from A's final state connect back to the starting state of S1. So here what will happen is, if I want to repeat A 3 times, first I will come here with epsilon A, again I will come here A, again I will come here A. So this is the final state, it will get accepted. Okay, suppose that you want to repeat 0 times. At that time what you do, since this is the starting state as well as the accepting state, what you can do is do the epsilon operation here. Okay, so that it will be repeated in 0 times, right? If you start from here and end here only without passing through A, so no A will be printed, and that will satisfy the criteria that it should be repeated 0 or more number of times. Okay. So for 0 we will do the epsilon operation on the starting state. Now let's look at the question. The question can be given as follows: B union AB, then the whole star. Break this down into small modules. Here we have two letters A and B. So make the FSM for A and B. After that, what is the first operation? Here it's AB. AB means concatenation. How do you concatenate A and B? Place A here, starting point to the ending point of A, connect with starting point of B, that will be the concatenation. Now for B union AB, how do you do the union? This one string here and B is one string here. Between this string and this string, how can you make a union? Firstly, you have to create a new state here, then connect it with the starting state of each of these via epsilon. This is a union operation. After we have our FSM here, if it's repeated n number of times, see this is done. B union AB is over. If it's repeated n number of times, how can we achieve that? We have discussed here, create a new state which is accepting state as well, and then connect the final state with the starting state. That's what we are doing here. New state, connect with the starting state, and each of these accepting states are connected with the starting state of A. Okay, not A, I mean this one. Okay, so connect this with this and this with this. That should be through epsilon. And also along with that we have a new state here which is connected with the starting state of this diagram via epsilon. Okay. Let's move on to the next one. Here we have the concatenation as well as the union. Okay, so make A and B here, and then draw the FSM for A concatenation of A and B. Draw the A union B FSM here, and after that our final step is to draw the FSM for the repetition of A union B. Okay, so it's about repetition. Make a new state here, connect with the starting state of A union B, and then connect the final state of A and B to the starting state of this diagram. This will be the FSM for A union B whole star, and this is the FSM for AB. Now of our step is that we have to concatenate AB and A union B whole star. For concatenation, connect the ending state of this one with the starting state of this one. That's what I have done here. This AB and this is A union B whole star. Connect via epsilon. Okay. The next topic is to build a regular expression from a finite state machine. Okay, so this is the finite state machine given to us. We have 0, q1, q2, q3. This is starting state and the final state. Okay, so if you have to build a regular expression from the FSM, what you have to do is first eliminate the dead state. That means whichever state has no outgoing means the arrow, that we can eliminate. Okay, after elimination we will be left with the two states here, q1 and q2. Then it's upon us, like we can either eliminate q1 or q2. If you eliminate q2 here, what will happen is, but before that we need to change the final state here, I mean the starting state, because the starting state is accepting the values also, like 1 from here and 0 from here. Therefore we'll create a new starting state null here, which will be connected with this diagram here. Okay, so this is the starting state now. Now what we have to do is, observe here, it's going through 1 and coming back to 0, 1 0, right? So we'll eliminate 2 and write here 1 0. Same thing goes for here also, it's going through 0 and coming through 1. So 0 1 I'll write here. So this is it. This is the starting state which we made now only, passing through epsilon and reaching q1, which is having the 0 1 and 1 0. Now making the regular expression from this, it's pretty simple, because either the final state will have 1 0 or 0 1. Therefore we'll write 1 0 union 0 1, and this can be repeated n number of times, so therefore I'll have a star here. Okay, this is the basic method of building regular expression from finite state machine. Okay, so these are the steps followed. If you want, you can read this one. Okay, so let's solve another example. Here we have 1, 2, 3 and 4. Starting state, ending state connected with B's and A's. Okay, so we have to eliminate any one of these. So here we have to eliminate any one of these from this diagram. Okay, So what we have, what I will choose to eliminate is 2. If I eliminate 2, what is the path going through 2? B, B. Instead of that, I'll just write directly B, B. There is one more path to 3, which is from A. So if I want to reach from 1 to 3, I can go through BB, or I can go through A, right? So I can write A union BB. Okay, union means OR operation. And the same thing goes for 3 also. Here A union BB, then I can repeat B n number of times, then pass through A. So these 3 are concatenated, and B is repeated n number of times, so therefore it is B star. And this is the concatenated final result. So whatever you get, the result between the start state and the final state, that is the regular expression. Okay. Let's discuss another example here. Here we have two final states as well as one starting state. So let's see how to approach this question. Okay, since the start state is also accepting values, create a new start state. So here I will create a new start state which will be connected with this one via epsilon, and then it's having two final state, so therefore it cannot have any it cannot have two final state. We should have only one. What I'll do is I'll create a new final state, connect this with the new one, and this also with new one, and the connection is made via epsilon, and then remove the two final states from here, because this is the new state, right? After that we'll be removing 1, 2 and 3, because we just need the starting state and the final state. When we remove 1, 2 and 3, first we'll start from 3. Observe here carefully, it's coming through A, then A is repeated n number of times, then B. So that's the same thing we'll write here. Along with that we have B from 2 to 1. So from 2 to 1 we'll have A, then A star, then B. So A star and B, and union with B. So B will be written here plus or union. Here we will have A star B, which was through 3. Okay, and we have two states now, 1 and 2. Both we have to remove. First we will remove 2. If we remove 2, this will be the equation we will get, and if we remove 1, then we will get the final equation as this one. Okay. So let's learn about the applications of Kleen's theorem. In Kleen's theorem, we have the intermediate states are getting considered here. If there are no intermediate state, that means k is equal to 0. K denotes the number of intermediate states. If k is 0, we'll have a starting state and the final state. Okay. R of ij raised to k. K means number of intermediate states. If it's 0, here I will write R of ij and 0. Okay. And R is nothing but the regular expression. And if I and j are different, means I is not equal to j, that means there is a starting state and the ending state. Between that there is a connection. Suppose that I is equal to j, that means the starting state and the final state are same. So I'll have a self proof here. We have two possibilities, either the I and j are not equal and I and j are equal. And these two cases are under the case k is equal to 0. That means no intermediate state. Okay. So we have the different subtopics under this one. This is I is not equal to j. This is I is equal to j. If I is not equal to j, we have three options. Either I and j are not connected, I and j are connected by a single letter, or by multiple letters. Okay. If it's not connected, it means RE is equal to null, and if it's connected by a single letter, RE will be equal to that letter, and if it's connected via multiple letters, RE will be equal to A1 plus A2 till AK. Okay, means how many states are there. This is for I is not equal to j. Suppose that if I and j both are same, that means the starting and then ending state is same. At that time, use the same notations here: null plus epsilon, A plus epsilon, A1 till AK plus epsilon. So if it's same, you just have to add epsilon. Why? Because if you are ending starting from the same state and ending with the same state, that means you have passed through empty string, right? That should be included here. Okay, that means null string here. Considering the case where k is equal to 1, that means there is at least one intermediate state, which is k in between I and j, and k can be 0 or more occurrences, right? If k is repeated 0 number of times, it will be I and j here. If it's repeated 3 times, it will be between I and j, it will be 3 times k. Okay. So the equation will be as follows. What is the starting state? R of I, ending state is j raised to k minus 1. K minus 1 because k is equal to, it has not occurred, right? So it will be equal to k minus 1. If it's occurred at that time, what we'll do? How many times it has occurred? 3 times. So it will be r of I k. From I to k it's not repeated, right? So it will be k minus 1. Same thing goes for here also. K to k, k to k, k to j. So as you can see, k to k is repeated here. So you can write there as star. Okay, this will be the simplified equation from I to k and from k to j. I to k, k to j. In between that, we are repeating k to k n number of times. So we'll have k to k here raised to star. Then the final expression, considering the case 1 and case 2, will be this one, r of ij k minus 1 plus r of ik, this one, r of ik k minus 1, r of kk k minus 1 raised to star, and r of kj raised to k minus 1. So this is the final expression you will get after combining case 1 and case 2. Okay, so let's see an example here. In this example we have two states, 1 and 2. One is the starting state and 2 is the accepting state, and in between we have the transitions, the self loops among 1 and 0. Okay, so firstly we will be starting from k is equal to 0. That means no intermediate states. We will be considering all the possibilities from 1 to 2, from 1 to 1, 2 to 1, and 2 to 2. So if it is 1 to 1, 1 to 1 means it's passing through here. Either it could be epsilon or 1. So I'll be writing here 1 plus epsilon. Plus means or. Okay. And 1 to 2 I have 0, so I'll be writing here 0. 2 to 1 there is no possibility, so I'll be writing here null. And from 2 to 2 it is 3 possibilities, either 0, either 1 or epsilon. This was for the case where there is no intermediate states. In case there are intermediate states, we have to consider k is equal to 1. And here we will have 4 possibilities. K is equal to 1 for this one, then this one, then this one, and finally this one. So this is nothing but 1 1. Okay, this is 1 1. R of 1 1, k is equal to 1, so I'll write here 1. And according to this equation, what you'll get is 1 to 1, which is k is equal to 1. So R of I into k. R of ik means, sorry, it's ij. J is also 1 because it's having the self loop. So I and j value will be 1 as well as k value will be 1. So here we will get r of 113 4 times, which is nothing but 1 plus epsilon. How to simplify this one? This is the equations which we have. Epsilon plus r, the whole star is r star, and similar equations we have here. By using these equations, we will be simplifying this equation. When we simplify, we will get 1 plus epsilon the whole star. This could be further simplified as 1 raised to whole star because of the first equation. Okay, instead of r we have 1, therefore it will be 1 star. So this is the equation which we got 1 star by considering r11. Now we'll consider r12. We'll substitute the values, we'll get 1 star 0. Same thing goes for 2 1 and 2 2 also. We'll get 2 equations here, and by using these equations we'll be forming the final regular expression. What is the formula of final regular expression? This is the formula which we studied now. R of ij raised to k is equal to this formula. I is 1, j is 2, and k is 1, I guess. Okay, so this is given here, it's 1 only, and by using these values of k, sorry, it's 2 because we have 2 intermediate states in the second equation. By using this one, we'll simplify the expressions which we got here. Okay, by using these equations. When you simplify, you'll get the final answer as 1 star 0 concatenated with 1 or 0 plus. Okay, plus means 1 or more times. Okay, how do we simplify this one? 1 star 0 is there, that's written same as here, and here we have the same thing repeated 0 or more times. So this one can be included in this one. Okay, but it will be plus. Why it is plus? It is plus because at least 1 or more time it should be there. So if I want, why we took 1 or more time? We could have taken 0 or more time. But according to this equation, what you can observe is at least 1 time it will be there, right? This we can eliminate by taking star as 0. then this will be remaining. So at least in this equation, means anyways there in this equation will have at least one time this will be repeated. So I have taken plus here one or more time. How can we simplify this one? Separate this one here by using the equation 1 plus 0 raised to plus. Here it will get substituted as, here it will get substituted as, the epsilon will be removed, so it will be 0 plus 1 raised to plus, and this one can be taken as common. So here we'll have 1 star 0, then 0 plus 1 plus. So this is the simplified equation of the given question. The next topic is regular grammars. Okay, so it can be defined using four variables here, which is the first one rule alphabet, set, and the rule and the start symbol. So V is nothing but rule alphabet. Okay, here we will have terminal and non-terminal. Terminal means the lowercase letters and the non-terminal means the uppercase letter. Okay, so we'll discuss about this in detail in the upcoming topic, but for now we will discuss the rules. Okay, and sigma is the alphabet set, and R is the rule, means x to y or y to x, and S is the start symbol. Let's understand these rules by an example. Here the example is L is equal to W belongs to A comma B, and the length of W is even. Even means there should be at least two letters, 0, 2, 4, 6, 8, those type of letters. Okay, so S can be either A or B or even epsilon. So I'll write here S goes to epsilon. S can be either A and B. Okay, and after that it should be even letters. So one letter is getting here, but other letter will come through T. T is a non-terminal. That means from T we can have A or B. Okay, when we use T here, either I can have A or B, right, to make the combination. So after we get here A or B, it should be keep on continuing to accommodate all the possible even numbers, right? So we'll have again with S here. S can be substituted S can be substituted using epsilon or any other combination. Means again we have to generate. If you have to generate AA, BB or any other pattern, you can generate using S. Okay. So this is how we define the regular grammar for the given expression. Let's move on to the next one. Here we have the strings of A's and B's that end with A, means 4 A's. Okay. So if it end with 4 A's, we have to accommodate the 4 A's. Okay. So let's start from here. S goes to AT, and T goes to AZ, Z goes to AY, and Y goes to A. So here we have 4 A's. For the other letters like A or B, we can have S goes to A. Here it should be S, right? I have forgotten to put here, but here we will have S here. Okay, so A goes to AS and S goes to BS. So n number of A's and B's could be repeated here, and then when ending we can go to this loop. Okay, means it will be 4 A's. Then the regular grammar to FSM. Now we have studied how to generate a regular grammar. Now how to use this sentence to change to FSM, means the finite state machine. Let's consider an example. Strings that end with A. We have written the rules here. By using these rules, we have to find out the FSM for it. Okay. So first write S goes to B, C, D. Right. So write here S, B, C, D. The unique states here, which is S, B, C, and D. How is S connected to B? S is connected to B via A. So write here A. B is connected to C via A. Write here A. Same thing goes for here and here also. But D is just connected to A. Here we have nothing. So make a hash here. Make it as final state and double circle it. Okay. And in the starting place we have also A and B. Right. From S goes to S via A. S goes to S via B. So we will have S the self loop A comma B. Okay. This is the starting state and this is the ending state. Then another example is the missing letter language. Okay, that means you have to define all those possibilities like the missing letter from A, B, and C. That means the string should not have a particular letter. Okay, that will be the acceptable string according to this language. Okay, so what are the possibilities? Here we have the three states A, B, and C. S goes to A means if it goes to A will not be there. That's the rule we defined. Okay. So if A is not there, that means it will be BC. Here also the self loop BC. So B and C will be repeated n number of times without A. If you want without B, go to the state B. Here we will have AC and the self loop will also have AC. Same thing goes for C also. Here we'll have AB and C will not be repeated, so it will be AB. Okay. How can we define the strings here? S goes to epsilon, and S goes to epsilon because we can have an empty string also, and S goes to A, sorry, S goes to B via A. See, what I mean is S goes to B. Okay, B means this state via A. Okay, and via A it can go to C state also. Then through B, where it can go? Through B it can go to this one and this one, means A and C. So I have written here A and C. And S goes to via C, where it can go? Via C it can go all the states except C, right? So this one and this one, A and B. After writing this one, from A and B, which all states are possible? A via B again to A. Okay, means ABA, A via C to A. That means ACA. Okay. The same thing goes for B and C as well. After we have written this one, this will form the regular grammar for the given FSM. The next example is of the satisfying multiple criteria. Here W contains an odd number of A's and W ends with a Y. Okay. So it should contain odd number of A's. Okay, it does not say about B, so we'll have an infinite loop for B, but for A it should contain odd number, right? For that, what we have to do is we have to write here T. Okay, T is the state through which the loop can be ended. If S is equal to AT, one A has come, then T can be ended. Okay, that means only one A will be there. That will be a valid string. How to remove the even number of A's possibility? That we can do by passing again to S, right? From A, if I try to make a even string, what will happen is A to T, one A came, again from T to AS, so 2A came. After 2A came, it should not end. So currently it is in S, it will not end because S is not connected to any of the epsilon. Which is connected to epsilon? T. So if I have to end the string, I should again pass through A, right? So then only I'll be able to reach the end of the string, right? Again 80, then it will be 3A, right? So for that I have written this criteria here. Also we have to include the criteria for B. Okay, for B what will be the case is T goes to Bx, okay, and X goes to Bx again, means X will not be the criteria for ending the loop, otherwise only B will be there. Okay, that should not be possible because W contains an odd number of A's, right? So at least one A should be there. So to ensure one A is there, we'll pass X through AS, then only it will be possible to end the string, right? If it goes through AS, then it will go through from S to T, then from T it will go to epsilon. Okay, so at least one A will be there, that will be confirmed. If I just enter via X, at that time what will happen is no A will be included, and it will negate the criteria that W contains an odd number of A's. If no A is there, that means 0A, which is even number, right? So that's why we have not put any epsilon via X. Okay. The next one is the regular grammar and the regular languages. Okay. So if you have to convert our regular grammar to FSM, what we'll do is we'll write the regular grammar here as we seen above, and after that what we have to do is observe the unique states which are S, T, Z and Y. Write here S, T, Z and Y. Then from the equation see which is the transition going through it. Okay. For example, S to T it is A, right? S is equal to AT. Write here A. Same thing goes for the other loops also and the other connections, and the final state will be connected to hash. Okay. Here's an example: string that contains A and B of even length. Even length means there should be at least two. Okay. So this is the starting and the accepting state. If I have to end the string, I have to reach A. To reach, I mean we have to reach S, right? To reach S, I have to pass through T, again come through T. So no matter how many times I pass, I'll do it double, right? If I take A, I should again come to S, right? So I should take B or A again. So the length of the string will be multiples of 2, right? So it will ensure the string is of even length. Here's another example: strings of A's containing any number of A's. Okay, so it can have 0 or n number of A's. So I'll have S is equal to S goes to epsilon, or S goes to AS. So I can have any number of A's here by using this equation. Okay, so this is the self loop. in which the starting and the final state is the S here. Okay. And here the string of A is consisting at least one A. At least one A means I should have a state here which goes to final state, which will be having at least one A. If I want 2A, I'll pass through a self loop, then go to the final state. If I want 3A, pass through the self loop 2 times, then pass through this one. If I want 1A, it will pass through this one by default. Okay. So this will satisfy this criteria. Okay. And similarly, if I want to generate the multiples of 3, like A should be repeated 3, 6, 9, 12 times and all. So I can have here A to A, then A to B, B to A. So reaching S, I should pass through 3 A's. 3, then if I have to pass again 4, I can't reach the final, again not final, then 6th time I'll reach the final, right? So this is how you make the FSM out of the regular expression. Here is a similar question in which we have to obtain a grammar to generate the strings of A's and B's with at least one A. Here B is included, so I'll have a self loop for B also, and the ending position will be gone through A only. Okay. Coming to regular and non-regular languages, the difference is that in regular languages it can be expressed in the form of the regular expression like BB, ABB, double ABB, triple ABB. So the pattern you can observe here in regular expressions, right? BB is repeated in all the equations, but A is getting repeated, means increased one by one. Okay, means 1 time, 2 time, 3 time, and so on. Okay, so this can be expressed in the form of A star. Star denotes 0 or more times. So I'll have 0 time here, 1 time, 2 time, 3 time, and BB is constant. So this is known as regular language. Okay, because this is expressed in the form of equation. Okay. And non-regular language is that which cannot be expressed in the regular expression. For example, if A and B are appearing equal number of times, like AB, double B, triple B, and so on, this cannot be expressed in the form of star or plus, because star means 0 or more. If I use 0 or more for both A and B, I can also have the string double A triple B, right? But that is not valid. So therefore, whichever expression I cannot express in the form of regular language, it's called as non-regular language. To express that, we will use n. Okay, this one can be expressed in the form of a raised to n and b raised to n for all the values of n greater than or equal to 0. Okay. Then we have the closure property, which is same as we have discussed before. If A and B are regular, A union B is also regular. Concatenation and complement, and they are closed under intersection, difference, reverse, and letter substitution. Okay, so this is the same thing as we have learned the previous topic. And the next topic is very important one, which is showing that a language is not regular. Remember these 3 rules. If W is equal to XYZ is a string here, and X belongs to, means it can be expressed in the form of X, Y power I, and Z. Length of Y is greater than 0, XY is less than n. Let's discuss this by an example. Show that A power n, B power n is not regular. Okay, and the criteria given is that A power n and B power n can be substituted with A and B. So what is the rule is that whenever you create a string here, divide into 3 parts. That's up to you how you divide. I have divided A as X, B as Y, and another B as Z. Okay. So what I have to do is I have to pump the Y value. That means increase this B value. Y is equal to B I have taken, increase Y value. Like I can make it as 2B, 3B, 4B, or 5B. Okay, like n B's. If I make as 2B here, what will be the string? AA same as this, B same as this, and here I have 2B. Does this string belong to the letter L, which is defined here? A power n, B power n. A is 2 times here, but B is 3 times. That is against this rule, in which it says A and B should be repeated n number of times. So if it does not belong, it's not a regular language. Okay. The same thing is applicable here also, showing that balanced parenthesis is not regular. It's simple. Just take Y as a opening braces or closing braces, and then repeat it n number of times. If I repeat n number of times, then the count will be deferred, right? Means the opening braces are more, closing braces are less, so it does not belong to this language. Therefore, it's not regular. Okay. See, it's very simple. Take X and Z. In between that, take any character as Y. increase that character n number of times. Then check if that belongs to the language or that belongs to the language or not. If it belongs, it's regular. If it does not, it's a non-regular. Okay. The next one is showing that it's a palindrome or not. Okay. Palindrome means if W is a string like ABC, reverse of W is CBA. So what is palindrome? ABC, CBA. So what we can do is take any letter in between, repeat it n number of times, then check if it's a palindrome or not. For example, AA, BB is a palindrome. Choose B here, repeat it 2 times. So it will be AA, triple B. If I do it in reverse order, I'll get as BBB, AA, which is not same. Therefore, it's not belonging to L, and it's and thereby showing proving that it's not a palindrome. Okay. Here we have to show that a language with more A and B is not regular. If there are more A and B, if that's the criteria, take Y as B, increase B more than the times of A. Like for example, A is 4 times here, make B as 4 times here, and then 2 is from here by default. So total number of B will be more, right? So when B is more, it does not belong to the language which says A should be more. So therefore, if it does not belong to the language, that means it's not regular. Okay, so this is pretty much it about module 2. Let's go through the PYQs and discuss what all the questions we have solved, which are left, and which is the important topics. Okay, the first one is define regular expression. Okay, that's in the definition I've written in the notes. Write a regular expression for the following. Okay, here W does not end with VA. See, if we get a question like it does not end with a particular letter, what you have to do is construct a RE for it ends with BA. After that, change the final state into non-final state and non-final state into final state. If you do that, we'll obtain a expression which is satisfying the given criteria. Okay, and the decimal encoding we have discussed, and converting the FSM to the regular expression. The same example I have taken in the explanation also, you can refer to that. This also we have done, and the pumping theorem, which is nothing but the last topic which we have discussed, does the same thing, and show that the language A power n, B power n, that's also done, and regular grammar, and with at least one A, having the strings without AB, zeros and ones with 3 consecutive zeros. This also can be easily found and done by using the grammar rules like S goes to A and B by using the regular language. Convert the NDFSM to design NDFSM to accept the language. This one, okay. Here we can, what we can do, union operation and concatenation, as well as clean star, right? So by using this, we can create the FSM. And here we have the same thing here as this one. We have to convert this expression into NDFSM. So basically, observe what are the operators here: the union operator, concatenation, as well as clean star. So do it one by one. Like make a FSM for the single thing like 0, then make FSM for 1, then find out how to make the connection between the both individual FSM that I have explained in the topic of concatenation and union. Okay, you can refer to that. The next question is, if the regular grammar defines exactly the regular language, then prove that the class of languages that can be defined with regular grammar is exactly the regular language. For this question, we need to define 3 rules, which are non-terminal to terminal, non-terminal to terminal, and non-terminal, as well as the last one, which is non-terminal to epsilon. By using these 3 rules, give some examples which are relevant, and also you have to include the union, concatenation, and the difference, clean star, and the negation operation. Okay, by using those examples, prove that, like firstly we'll have the rules of grammar here, apply the same thing for the language, and show that both are equal. Okay, so doing that will prove that the regular grammar can be used to create regular languages. Okay, the next one is prove that the regular languages are closed under the complement intersection difference between the difference and letter substitution. Okay, this also we have discussed in the theory explanation. Convert construct NFA This also is done. And show that 0 power n is not regular. See, n is prime, right? Prime means take as 3. 0 power 3 means 0 0 0. Take it as xyz. Repeat y n number of times. So it will become 4. 0 0 0 0. That is not prime. 4 is not prime, right? So it will be not regular. Okay. And use the Kleen's theorem for the finite automata. This is the state elimination question. First eliminate 3 and write what is the where it is passing through. Do the same thing for 2 and 1 also. Okay. And the last two questions are just the explanation of the Kleen's theorem which I have discussed, the union, concatenation, difference and the complement. Okay. So this is it for the module 2 of 18 CS 54, and thank you for watching. I'll see you in the next one.